The last time we talked about horizontal asymptotes, we talked about a constant value divided by some increasing function has a horizontal asymptote at 0, and then if you want to, you can shift it up and down by however much you want. But what happens if you have a more complicated rational expression like this? We've got a sixth degree equation, a sixth degree polynomial on the top and the bottom. Does this have a horizontal asymptote? What is it? How can we know? So that's what we're going to talk about. And there are some really easy tests that you can do to answer that question if that's all you care about. But this builds towards some more sophisticated ideas in calculus. So if all you do is memorize a shortcut, it's probably not going to be very helpful for you in the long run. I'm going to introduce an idea that's going to be sort of an informal idea for now, but it's a pretty powerful one, and it's the idea of a dominating term. So let's think about what happens as x gets larger and larger and larger. In fact, let's imagine plugging in larger and larger x values and evaluating what is the function. So when I plug in larger and larger x values, I'm going to get some number in the numerator divided by some number in the denominator. So I want to know which of these three terms has the biggest influence on what this number in the numerator is going to be. So obviously x to the sixth grows much faster than a single power of x or this constant. So this is what we call the dominating term of the numerator. What is it dominating? It's dominating all the other terms in the numerator. And it's called the dominating term because it's the term that grows the fastest. And what that means is that as x approaches infinity, this number is going to be much, much larger than these. These will be kind of minuscule. They'll be almost like rounding errors compared to this value. So if I want to know approximately what is my function equal to for very, very large values of x, I can just ignore these, because the contribution from these terms is going to be so small compared to the dominating term that it's right to say for very large x, my function is approximately equal to this. So same thing in the denominator. In the denominator, my dominating term is this one. And be careful, it includes the coefficient, which is -2. And again, it's fair to say it's not true that f of x equals this. I'm saying that f of x is approximately equal to just the dominating terms. And it's approximately equal to the dominating terms only for very large x. So I think if you're writing this algebraically, you would say something like f of x is approximately equal to this for x. And then you might not have seen this notation before, but if you have like if you have two greater than signs, that means much greater than. So for x much greater than 0. Okay, so wait, how does this help us? Remember, we're trying to find the horizontal asymptote. The horizontal asymptote is what the y values are doing when x gets really big. And we've said that the y values are approximately equal to 3x to the sixth divided by -2x to the sixth, but only when x is really big. So if we look at how this simplifies, the x to the sixths divide each other out, and so we just have -3/2. So what that means is, as x gets really, really big, the y values are approximately equal to something that turns out to be the same as -3/2. So all of that means that your function is approaching -3/2 as x gets really large. Some people call this an end behavior model. It's a model because it's approximately equal to your original function, but only for the purposes of finding the end behavior, what's happening when x is very large or very negative. Okay, you give it a shot. Find the dominating term in the numerator and the denominator, make a simplified end behavior model, and decide what do you think the horizontal asymptote is. Okay, here's the answer. So dominating term in the numerator is the term that is growing the fastest, which is this one. In the denominator, you might think it's the one with this big coefficient, but it's still the one with the largest degree. because it doesn't take very large values of x before x to the 7th becomes larger than 9999x. If you imagine this is like a very steep line, but this is a curve that gets steeper and steeper and steeper. So eventually it's going to cross the line. Okay, so what we have is that our g function is approximately equal to negative 3x to the 7th divided by x to the 7th, which is equal to just negative 3. So that's told us that we've got a horizontal asymptote at x equals negative 3. What about this one? So, well, here, why don't you take a guess first, see what you can come up with. I'll give you a hint. You can solve this problem without actually multiplying all of these things out. All right, so dominating term in the numerator is the 6th degree term. In the denominator, you of course could square each of these things and multiply this whole thing out, and you'd have a 6th degree polynomial. How do I know it's a 6th degree polynomial? Because here the highest power of x is 2, because I'm squaring it. So this is going to produce something with an x squared in it. This thing is also going to produce something with an x squared in it. This thing is also going to produce something with an x squared in it. When I multiply all those together, I'm going to have x squared times x squared times x squared, which is an x to the 6th. So I know that if I was going to multiply all this out, my highest degree term would be an x to the 6th. What would its coefficient be? Well, let's see. The coefficient of all of these is just 1. So if I was just going to if I'm going to keep the 2 on the outside here and I'm just going to multiply all of these out, I'm just going to have a single power of x to the 6th plus a whole bunch of lower degree terms. So then if I multiply the 2 in, I've got 2x to the 6th plus a whole bunch of lower degree terms. So I don't actually have to multiply the whole thing out in order to know what the dominating term is going to be, because all I have to do is figure out what's the highest degree term and what would its coefficient be if I was going to multiply all of them out. And I don't really care what all the lower degree terms are, so I don't need to actually do the multiplication. I just need to think, what would the x to the 6th term be? So that actually solves the problem. So now I know f of x is approximately equal to 3x to the 6th over 2x to the 6th for very large x, which is exactly equal to 3/2 again. So we've got a horizontal asymptote at 3/2. Let's do one last one. What about this one? So here I've got these as my two dominating terms. So I know that for very large x, f of x is approximately equal to negative x to the 7th over x to the 6th, which is the same thing as negative x. Well, what does that mean? Remember, this is an end behavior model. So what I'm saying is for very large x, my original function behaves like it's this thing. So in the other examples, it behaved like an expression that was just constant. And so what that means is that we don't know what's happening in the middle of the function, but for very, very, very large x, it meant that the function behaves almost like a constant, because when you simplify the dominating terms, it became constant. For our example here, even though we don't know what's happening in the middle of the graph, we're saying that when x gets very large, it behaves like negative x. And negative x is this linear function here. So we don't know what's happening in there, but we know that for very large x, our y values are going to behave as if they're just the function negative x. And what does negative x do as x approaches infinity? Well, it decreases forever. It decreases without bound. So what our end behavior model has told us in this case is that there is no horizontal asymptote. Instead, there's what's called a slant asymptote. There's this kind of line, and our y values are approaching that line. So notice, don't try and zero in on rules. Don't try and say, oh, it's just like this number divided by that number. Think about the meaning of what's going on, because if you think about the meaning of the end behavior model, you should have been able to come up with this on your own. But if you're just trying to memorize like number divided by number, then when you get x over here, you're like, that's not a number. What does it all mean? So try and keep your head up for what are the underlying concepts and think about what would they mean in these different kinds of circumstance.